All right, so now that we have a heuristic, picture of, let's work out more of the details. Okay, suppose we have, suppose, uh, we have chosen a path. So this is important to keep in mind. And on this path, we look at xn, tn, xn minus 1, tn minus 1. So because we are not doing the sum anymore, because we have chosen a particular path, what we have to do here is that we can write e to the power I by h bar s n minus 1, but here we need a normalization factor for dimensional reasons, okay? So why is that? Because we have done this kind of normalization, right? That means that this is dimensionless, this has dimension of length, then this has dimension of inverse length, right? So that means that, and of course the exponential is dimensionless, that means that 1 over w delta t means here, it means that w is a function of delta t. This has dimensions of 1 over space, or 1 over length, which is really length. Okay, so it's important to realize that we are just taking one path, and that's why there's a sum here. Okay, so now the assumption here is that, again, this is an assumption that is motivated by quantum mechanics, because in quantum mechanics, that's how it turns out. The assumption is that W, only depends or depends on, is independent of the potential V of x. And you might say, how did we guess that? Well, that's because we actually know the expression of the propagator from quantum mechanics, and we can just look it up. And we can see that, oh, there's a normalization there which does not depend on the potential. So, you're allowed to assume stuff like that. Okay, so this is not a very major assumption, but but it makes life easier. So what we are going to do is that we are going to evaluate W delta t in the limit in which delta t goes to 0, or in the limit where n goes to infinity. Okay. So in this limit, we can approximate the path as a straight line segment. If I do that, then I can express the action, which is an integral from t to the power tn minus 1 to tn d of t. Remember that this is done for a particular path. mx dot squared divided by 2 minus v of x. This thing can be written as, this is just delta t. right? And m is a constant, and the difference in x is xn minus 1. This is squared divided by delta t squared. This is the discrete version of the time derivative. We are basically discretizing the whole thing. xn minus 1. Here we are taking the value of the potential energy at the average, at the midpoint. Okay, in the limit where these points collide, it's not going to be relevant. So the thing is that, so because we've assumed that Wt is independent of Vx, we can calculate this for the case for the free particle. So we can compute this for the free particle. We put V of x equals to 0. So for the free particle, this expression becomes xn Tn, xn minus 1 Tn minus 1 equal to 1 over W delta T times e to the power I, and within brackets, m xn minus 1 squared divided by 2 h bar delta t. Okay? We're just setting this guy to 0, that's all. Okay? So on the other hand, if I look at this in the limit where the two times collide, so if I look at xn Tn, which is exactly what delta t goes to 0 limit, if I take xn minus 1, Tn minus 1, but set Tn equal to Tn minus 1, of course, this should be just because they are orthogonal states, orthogonal bases, this should just give me a delta function, right? So that means that the right-hand side of this equation, this guy should have an interpretation of a delta function. And of course it does, because it's a Gaussian. Remember that Gaussians are one of the representations of the delta function where this thing goes to 0. So everything is consistent. So of course, because this Gaussian needs to, this delta function will be normalized as this is, we just need to normalize this part, and that will just yield the value of W. So we just need to do a delta function integral. So the delta function integral is from minus infinity to plus infinity, e to the power I m. So what we will do is that we will just replace this thing by a variable, say psi squared divided by 2h bar lambda t delta t del of psi. And we know we have done enough Gaussian integrals to see that this is going to be just this thing. And therefore, we find that 1 over W of delta t is given by square root of m divided by 2 pi I h bar delta t. Okay? And therefore, so what we are using is that in the limit where delta t goes to 0, this factor, sorry, I'm being lazy, this factor times e to the power I m psi squared divided by 2h bar delta t is nothing but the delta function. So we can now put all of this together, and remember that although we derive this normalization factor for the free particle, but it should be valid for all particles. by assumption. So xn tn minus 1, sorry, xn tn, not minus 1, xn minus 1 tn minus 1 for a particular path is going to be the limit where n goes to infinity, m divided by, we are not taking n, we are just writing the result of our calculation. This is m by 2 pi I h bar delta t square root exponential of I by h bar Sn n minus 1. Of course, when we plug this into our expression for the propagator, we have to make sure that we take all the paths. And the way we take all the paths is that we integrate over these variables, right? So our total propagator from x1 to xn, t1 to tn, and x1 to xn is going to be, we have to take the limit because otherwise our approximation will not be valid. N goes to infinity. Normalization is m divided by 2 pi I h bar delta of t to the power big N minus 1 by 2. And then we have an integral measure, which is dx n minus 1, dx n minus 2, dot, 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 dx 2, I think. Although I wrote 1 in my notes. Yeah, it's 2. And then we have a multiple of small n goes to 0 to n, exponential of I by h bar, s of n minus 1. Okay. So where we're taking that n equals to infinity limit, but keeping the interval t minus t1 fixed. Okay. So this measure, this thing and this thing, usually there's a notation for this, and the notation is this: start at x1, finish at xn, big D, x of t. Sometimes this d is written as a curly d. Let's write a curly d. And this is defined to be the limit in which n goes to infinity of a normalization constant, which is m divided by 2 pi I h bar delta t to the power n minus 1 by 2, and then a bunch of integrals, dx n minus 1, dx n minus 2, dot, 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 d of x2. And if I put everything together now, then the path integral becomes xn tn x1 t1 is given by this integral d of x of t times exponential of I over h bar from initial time to final time with the classical Lagrangian, but evaluated on all the different paths. Okay, so this is the path integral, the Feynman path integral representation of the propagator. Okay. Okay, I want to close with some comments, but before that, let's take some questions. We'll do examples. So, this looks very mysterious, but, it can be computed in the most simple circumstances.